All right. All right. Good evening, everyone out there in YouTube land, so to speak. My name is Dr. Jenny Kristoff. I am a professor of astronomy and physics at Glendale Community College here in usually warm and sunny Southern California. This evening, not quite so warm. It is 9 degrees Celsius, which is 48 degrees Fahrenheit. And I am in the fabulous observatory dome here atop Mount Wilson in the dome of the 60-inch telescope. So we have a lovely dark sky right above me, which you will be seeing some of in a little bit. And this evening we have a few sights that we are going to attempt to see. The first one is Gamma Andromeda, which is a double star in the constellation of Andromeda. We're going to have a look at Mars, and then we're going to try and check out the central region of the Andromeda galaxy, M31, and also M32, a companion to the Andromeda galaxy, among other sites. For those of you who are joining us on the live stream, if you have any questions, if you have any comments you want to send our way, please do so in the chat. We have a wide open 2 hours. If there's something that you are desperate to see through the 60-inch telescope of Mount Wilson, by all means, chat that, and we will try and work it into our observing schedule. For those of you who want to see what the inside of the observatory looks like, here is a kind of wide angle view. I'm over here in my burgundy jacket, waving at you now. This gentleman behind me is Dr. Chris Burns, who is one of the astrophysicists at the Carnegie Observatories in Pasadena. We are fairly close together. I am not wearing a mask, but that's okay because he's my husband. There are 2 astronomers in the family. Yes, we are the nerds on the block. We recognize that fact. We've owned it. And coming up the stairs right now, who is not part of our family bubble, is Mr. Tom Meneghini, who is the executive director here at Mount Wilson Observatories, who's just peeking over on the left-hand side of your screen here. So this is the historic, famous 60-inch telescope. Obviously, it is longer than 60 inches. The 60 inches is the diameter of the mirror at the bottom. So how a telescope works is it points in the direction that you want to look. Right now we're looking at a double star. So the telescope's pointed in the direction of the double star. Light coming from those 2 stars comes down to the bottom of the telescope where the mirror is. And the mirror is not flat like your bathroom mirror would be. It's curved. And it's curved at exactly the right amount of curvature to reflect all of the incoming light up to a secondary mirror, which is, I'm not sure if you can see my little arrow, my cursor, but it's up at the top of the telescope where you can see kind of horizontal bands that go around the telescope. 3 of them. The secondary is way up there, and the light from the stars bounces off the primary mirror up to the secondary, back down to a tertiary, which means third mirror, and then it comes out the side. And Chris is going to head over and point to where that light is focused, and tonight it is focused on a special type of camera called a Cmos camera. And you guys are all familiar with digital cameras because most of you will have cell phones of some sort or other, or iPods or iPads or some sort of digital or device with a digital camera. Those digital cameras are kind of a more basic version of what we have here. This is called a Cmos camera, and it's taking all that collected light and sending it down the cable to our computers. So if I click over to the telescope view, you now have a view of exactly what we're looking at with the telescope. And I know It's not particularly impressive at this point. We're looking kind of on the top right-hand quadrant of your screen, a bit of a blur of orangey golden color. And what that is the, and we're getting it to the middle, and we're zooming in. This is our view of the double star. Unfortunately, it's not a great view. We have some atmospheric seeing, and we also have a telescope mirror that is a little bit warm. So we had been checking the forecast for days, and tonight was supposed to be raining in Pasadena. And rain down in Pasadena means that it'll be snow up on Mount Wilson. And when there's snow up here, they close the roads because most people do not have snow tires or chains on their tires. So most people cannot drive in the type of weather that we get up here. Lo and behold, this rain is going to come tomorrow night. So we only decided this morning that we were not going to cancel due to weather conditions. We actually were going to do this live stream. And we are up here with a slightly warm telescope mirror. And you're probably like, what do you mean the mirror's warm? Well, what we do is we have regular old-fashioned incandescent light bulbs underneath the mirror, and the light from two 100-watt light bulbs, so it's 200 watts in total, creates enough heat to warm the mirror ever so slightly above the ambient temperature. And what that does is it keeps condensation from forming on the mirror itself. Because if you get condensation on the mirror, you're not going to be able to see anything. It says that YouTube is not receiving enough video to maintain a smooth stream.
It's probably because we're
I suspect that's because we are looking at or YouTube thinks we're looking at a completely blank screen. Chris, can you grab the mouse? Because I can't do anything.
Sorry.
You've taken my Chris took the wireless mouse away, so I can't get back to.
So we can rotate the dome a bit because.
So we're back here. You get to see me again.
And why don't you give the large view and we'll rotate the dome?
Yeah.
We'll rotate the dome to.
Yeah. And what we're going to do is we are going to rotate the dome and then move the telescope, and sometimes that's loud. When it goes in this direction, it's not so loud. When it goes in the other direction, it's really loud, the dome rotation. And then we will move the telescope in order to focus on Mars, which is, of course, the great target that we have for this evening. With the conditions, the seeing conditions, and the slightly warm mirror, I'm not sure what we will be able to see of Mars. We'd be able to see details on Mars. I know with this telescope, we cannot see the moons of Mars because they're really quite small and Mars is quite far away. But both the dome and the telescope are moving. And I think you'll probably be able to see that on the feed that we have going now. I had no idea how cold it was going to be up here tonight, so I have like 2 hats, 3 scarves, 2 pairs of mittens and gloves, and got my tube for keep my neck warm and all sorts of things. But so far, I can survive without the hat. Chris, why don't you talk about that?
Okay.
Come. Yeah, come join me. We got 2 chairs here.
Okay, so as the dome is rotating around, yep, Jenny is pointing to a platform that's attached to the inside of the dome. And if you look at it closely, you can probably see that it's on rails, and those rails travel up the dome. Oh wait, I've got my laser.
You got your laser pointer?
My laser. Let's see if this works. All right.
So he's got a green laser pointer. There we go. Yep.
There we go. So these are
So why don't you take the laser pointer down to the top of the ladder? So there's the ladder
right here.
over here, and if you look at the top, he's got a little spot. There you go.
All right.
And now you can explain.
And this is the rail, and the rail goes up the dome so that this entire platform here goes up and down the dome. And the reason for that is while tonight we are observing through our camera, actually you can't really see the laser very well there, but so the light is coming back down the tube and out the side to where our camera is. But in other configurations, you can change the top of the telescope, which we call the cage, and you can put an instrument at the very top. And in that case, you're going to need to be able to get up there to do your observing, to put your instrument on and off and control it. And so you would be up there, you'd be on that platform in a chair or working at a desk. I think there's a desk up there. And the whole thing just goes up to the top of the telescope so you can do your work, and then comes back down. All right, so now
And those of us who are afraid of heights would probably send a colleague or an assistant to do the observations.
See how...
Yep. So Chris is checking to make sure that we have Mars. We've turned off some of the dome lights. Do I go back to the attic view? There we go. Oh, hello, Mars. Aren't you pretty? All right. So it actually looks pretty steady. Tom, what do you think?
It looks pretty good, but we have a ring around it.
There is a bit of a ring around that. What do you think that's caused by? Heat. All right, this is our warm mirror. So we we called up the mountain, because we didn't come up first thing this morning. Called up the mountain, and one of the residents who lives up here was kind enough to come in and turn off the lights under the telescope mirror. But Tom, you say it takes at least 24 hours to fully cool down? Yeah. Oh, yeah. So 12 hours is clearly insufficient. Well, it wasn't even quite 12 hours. We decided that we're coming up here about 9 o'clock this morning. So we have a beautiful view of Mars, which is okay. You can certainly see that one side of Mars, the right-hand side, is a little brighter than the left-hand side. And there is top to kind of, there's a darker area, kind of a bit of a dark stripe from the top center down to the left, I guess 2/3 of the way along the left side if you follow the curve around down to the bottom. Mars does have a lot of variations in color on its surface. The primary color for Mars is, of course, this reddish orange, and that is caused by the actual mineral on the surface, iron oxide. Iron oxide on the Earth, generally known as rust. On Mars, it's just the Martian surface. There are some questions about how so much iron oxide got onto the surface of Mars. But for sure, there'd be a lot of iron in the crustal material of Mars. And the theory goes that, hang on, Chris is doing something with the camera now.
Sorry, I'm just making sure that we've got the best settings.
We are checking the settings.
Okay. Yeah, I think we've got a very low exposure rate and low gain, so this is
The best we can do?
probably about the best we can do. Don't want to bring
Yeah.
it too around.
Now, is that in focus? Because it looks...
Yeah, so we're in focus, and I think what's going on is that halo is just a product of the mirror just being not quite maybe in the right temperature. We saw this before, so there I've turned up the exposure so you can see that there's sort of this halo around, and I'm thinking that's just
Heat haze.
heat haze. So I'm going to bring it back down again because Tom is trying to work on focusing this a little bit better.
Yeah, if you've ever looked atop your
Is that better?
barbecue, when you're barbecuing and you see kind of the heat haze coming off the barbecue, it's the same thing. This is why we don't want a warm mirror. And this is why, in fact, telescope observatory, like the dome, is never heated. That's why I've come with like three scarves and 2 hats and X number of mittens, because it's cold in here. And we can't heat it because then we'd get this heat haze, and that really affects the quality of the observations that we can do. So you can see the result of having a ever so slightly warmed mirror. It's not great what we're looking at. I have seen Mars look a little more focused, a little more steady with this telescope before. But we're going to do this again in 2 weeks. Our next observing session is February the 16th, so 2 weeks tonight, and it will definitely be clear, knock on wood. I've gotta wish into Mother Nature about that, and we will have the lights turned off the day before so that we can make sure we have a nice cooled mirror.
So we are seeing some features every now and then. So why don't we have a look at Stellarium and see what Stellarium says Mars should look like.
Okay, so what we are going to do next is head to a software package. Ooh, this is almost like Halloween. It is a red light, not an orange light. But we're gonna head over to a software package. I'm gonna show you what Mars would actually look like if we could zoom in close up with like the best telescope ever. This is a software package, so it's not actual real photographs, but it is using real data. So let's head over to Stellarium. And we are looking in the direction of southwest. And what I can do, where did my cursor get to? Hello.
It's there, it's just dark. Just
Where?
click and drag.
Where? Oh, there it is. All right. So we're heading east. That is not where Mars is. Mars is going to be in the south, and the horizon is down where the letters are, the SE and the S and the SW. But looking higher overhead, we have the Constellation of Orion. Where's my cursor? Why don't I have a cursor? I don't see a cursor.
It's on your other program.
Is it? Yeah, okay. This is, no, it's gotta be here somewhere because I can move around. I would really like the cursor so I know what I can click on, because I really want to click on Mars. And you said, Chris, it was very dark?
Maybe. Do you want me to do it?
Oh, there it is. Okay, so Mars, we can click in there and then zoom in. Now,
Just hit forward slash.
there we go. So this is Mars. Not sure this is coming through.
It is, it's just on a 15-second delay.
Is it? Okay. So this is what we have of Mars, and Phobos seems to be very close to Mars, and Deimos as well. But both Phobos and Deimos are actually really tiny objects. Phobos is the larger of the two. I think it's something like 21 kilometers in length, which is in miles, maybe 14 miles, and Deimos is smaller. So these objects are like city size, and from a distance of, what have we got now? Easily 100 million kilometers away, we are just not going to be able to see something this size.
It's 232 million.
232 million kilometers. That's how, well, no, that's how far it is from the sun. Distance from us is 181 million kilometers. Yeah, Chris, it's not coming through. Oh, now it's coming through.
It'll get it.
There is a long delay between what I'm seeing on my view and then what I'm seeing in the feedback that you guys are seeing. So there is a question of why do you change the temperature of the mirror? Just to keep the condensation from settling on the mirror. So if you ever take a hairdryer to your shaving mirror in the morning after you've had a shower to get rid of the condensation, warming the glass of the mirror up will evaporate the condensation. But if you keep your mirror warm, then the condensation never, well, the water moisture never condenses on the cold glass. So basically it's to keep the glass above the ambient temperature and above the dew point. So we're very careful of making sure things are covered if the humidity is high, but we're in Southern California and the humidity is hardly ever high. The humidity tonight is actually for Southern California pretty high. It's 37%. But back in September, when we were having the situation with the Bobcat fire that came very close to the Mount Wilson Observatory, the humidity was in single digits, like it was 8% humidity, which is insane. It was very dry, which leads to a lot of sore throats, funnily enough. Very dry skin. But it does lead to great observing astronomically. So we are now back looking at the view through the telescope.
Yeah, I guess maybe Stellarium is
And
just
I guess,
having trouble.
yeah, I'm not sure Stellarium is working for us this evening because it seems to be stuck. And the view that I'm seeing from the YouTube stream is Orion without the zoomed in view of Mars. So I am now back to, we're now back to looking through the camera attached to the telescope. So we're back looking at Mars itself with the telescope.
Oh, no, there, see? It actually,
Oh, now it's gone over.
So it looks like it's almost like a 30-second, maybe even a minute delay,
Yeah.
depending.
We're still getting, we are not professional YouTubers. We are not professional broadcasters. We're both astronomers. And this whole YouTube live stream thing is new and strange. And we are working to figure it out. So please bear with us. Thank you. Every time we do this, it gets better and better. We are going to be doing this twice a month through the end of May. If you want to look at our schedule, I will post it in the comments later, but if you want to look at our schedule, you can go to the Glendale Community College Planetarium's website, and you can access that simply by going to glendale.edu/planetarium. In fact, I will type that into the comments in the YouTube chat. So I'm going to say schedule for future live stream star parties is at glendale.edu. I can't type too quickly. My fingers are cold. Planetarium. All right. Did I spell everything correctly? I hope so. There we go. So if you go to glendale.edu/planetarium, you'll get to the planetarium website. Usually we welcome thousands of school groups, or thousands of school children on field trips into the planetarium every year, but obviously this year we can't with the COVID situation. So we've pivoted and trying to figure out the best way to do some outreach. So we came up with this idea of the live streams from your local giant telescope. Glendale Community College is just down the hill from the Mount Wilson observatories. It is the closest community college, and it takes approximately, I want to say, 43 minutes to drive here. Less than 45 minutes to drive here from the college. So we're very close by, and I have been bringing students and classes up to the telescopes to rent night on the telescope to give my students the chance to look through a phenomenal instrument and see some amazing astronomical sights. So I know the people up here at Mount Wilson, and they have kindly allowed me to do these field trip, the virtual field trip to the stars.
So we can move on to M42, I think, because that would look probably okay with this
Yeah.
smear.
Yeah, all right.
So we're going to go there next.
So we are going on to M42?
M42.
M42. Do you guys know what that is?
Now you got to wait 30 seconds for an answer. We'll see. By the time we get
Yeah.
there,
Well, I'll leave it out there. I'm going to ask you guys if you know what M42 is.
Let's go back to the inside dome view while we move the telescope.
Yep. Are you going to turn the lights on?
Okay, you're clear, so I will turn the lights on.
Woo! Okay, that'll destroy your night vision. Your eyes have suitably adapted to the darkness, and then all of a sudden the lights come on and your pupils go whoomph. But we do have the camera, which reacts much more quickly to the darkness again over what our eyes are capable of.
All right, and you may see that we have this big yellow ladder. That is what we use when folks come up here in person. And instead of having a camera, the Cmos camera in the position it's in now, we would have a big, huge eyepiece. In fact, I might just go fetch one of those eyepieces. So,
Ooh, to show everyone.
sure.
Yeah. So in pre-pandemic times, I would have a class. I would bring a class of astronomy students up here to this amazing observatory. There is a limited number of people that can come up here. The maximum size is 25. So my lab classes are capped at 24, plus me. It's perfect. So we come up and have an evening on the dome and look through the telescope with giant eyepiece. And here we go.
There we go. Now you can see Jenny upside down.
This is the largest eyepiece I've ever seen. Do we have a regular eyepiece to show them, like the little
yes.
1 1/4
Yes.
inch? So let me hang on to this. I've
Hang on to that.
never actually had the pleasure of hanging on to this on my own, but the diameter of this has got to be like, I don't know, 10 centimeters, which is 4 inches-ish. Is it a 4-inch eyepiece, Chris? 6. I lie. What do I know? All right. 15 centimeter eyepiece. So this is the Mount Wilson eyepiece. You put your eyeball up to there and you look through that. A regular telescope you'd buy in a store.
High-end telescope, because this is a 2-inch one.
Yeah, okay, you want to grab the 6-inch?
Yep, got it.
So a high-end telescope, telescopes that cost a couple $1,000s, have large, these are the large, regularly available eyepieces. This is a 2-inch eyepiece.
And to be fair, you can also get Dobsonians and less expensive telescopes that have 2-inch eyepieces.
Yeah,
It's just
there
a
we
question
go.
of the, I think we're getting close.
Cap the end.
So we're gonna go turn the lights back off.
Many telescopes, my own personal telescope that I ground the mirror of, that was fun, is half this size, or it's 1 1/4 inch. So it's a little tiny one. If you're old enough to be familiar with film cameras, the film canister that the 35 millimeter film came in, that diameter. that's the size of a regular eyepiece, not this monstrosity that they have, which is amazing to look through. But let's go see what the camera. Not yet. Yeah. Okay, hang on.
We gotta center this thing again.
All right, so you get me again in the Halloween view. Woo. All right, so I'm not seeing anyone telling me what M42 is.
So this is something you can probably do with Stellarium, because I think Stellarium is working.
Oh, we can try Stellarium. All right. Figuring out where we are. All right, so I'm back on Stellarium once again. My mouse has disappeared. So we're going to zoom out from Mars. Whoa. Okay. Okay, there we go. So here is the constellation of Orion. And if I can, my cursor is apparently invisible, which makes it really difficult to actually put anything on. There. Okay. So I'm going to click on Constellation Lines, and you can see the lines that I've added for the constellations. And a constellation, there are really two definitions of constellation. Traditionally, historically, a constellation was a pattern that a group of bright stars made in the night sky, as envisioned by many different cultures.
Sorry, I need to mess with exposure. Keep talking.
Keep talking. Okay, so that's the kind of old-timey definition of a constellation. Excuse me. The more modern definition of constellation is merely a patch of the sky. So modern astrophysicists, if they are going to, study something or publish their findings about a particular area that they were studying in the night sky, or if they want to talk to their colleagues, they need to be able to discuss where things are. So we have a coordinate system called the Equatorial coordinate system, which uses right ascension and declination. But the sky is divided into different patches. There are 88 of them in total, as kind of defined by the International Astronomical Union. And these are the constellations that a lot of people are familiar with: Andromeda, Pegasus, Perseus, Orion, Ursa Major, which has within it the 7 stars of the Big Dipper, Ursa Minor, the Little Bear. All of these constellations are kind of defined by not just the bright stars, but all the darkness around them. And the sky is divided into 88 patches, in much the same way that the country is divided into states here in the U.S., or provinces, or cantons, or whichever country you're in. And there is an imaginary boundary line. So here in Southern California, if you drove north, you would get to an imaginary line that would take you from California into Oregon. Is there anything physically there? No, it's just kind of what people have decided is going to be a boundary. So the same thing is true for the boundaries between constellations in the sky. I think we're back to trying to figure out where the cursor is in Stellarium. What you're looking at right now is the constellation of Orion. And you'll see in the center of the picture there are 3 bright stars. And from bottom left to top right, we have Alnitak, Alnilam, and Mintaka. Am I pronouncing those correctly? I have no idea. I do not speak Arabic. I do not speak ancient Arabic. Many of the stars were named by the Arab astronomers from about 400 CE, Common Era, so AD is what it's known formally as, and that was the golden age of astronomy, the golden age of Islam. Those Arab astronomers were amazing, and they named a lot of the stars, and we keep those names today. What we've zoomed into now is known as the Orion Nebula, because it is a bright nebula, or cloud of gas and dust, within the confines of the constellation of Orion. But to Charles Messier, who wanted to catalog some of the brightest objects and most interesting objects to look at, this was M42. So the M number in M31, M32, M33, M42, this stands for the Messier catalog. So Charles Messier was an astronomer that lived in the late 1700s, I believe, and he actually wasn't interested in this type of thing. He was interested in looking at comets. And the comets, he would be able to recognize, because comets orbit the sun, and so would seem to move with respect to much more distant background stars. So he would look at these fuzzy things. His telescope wasn't as good as this telescope. So he would look at these fuzzy things and make a note of where they were. And then he'd go back to them a week later and then a month later and see if they had moved with respect to the stars. If they had not, then they were considered deep sky objects outside of the solar system. And he was not interested in them. He only wanted to look for the fuzzy things within the solar system, being comets. But nevertheless, he cataloged some of the most fantastic astronomically significant observational targets. And this that we've zoomed into here in Stellarium is M42, which is the Great Orion Nebula. Now, there are stars forming within this huge cloud of gas and dust, but there is also a lot of light coming from this area, and that's because the gases of this cloud of gas and dust are actually glowing. Now, the really cool thing is that different gases can glow, or do glow, different colors. So a lot of the red color that you see, if you're looking at one of the fabulous photographs that the Hubble Space Telescope has posted online, that red is indicative of hydrogen. So hydrogen gas itself will emit 4 distinct colors in the visible portion of the electromagnetic spectrum. The red light that emits is by far the brightest. So there's also a yellow one and then 2 kind of bluey green ones. But the red is by far the brightest. So whenever we see red in outer space, we're like, that's probably hydrogen. Simply because 80% of the universe is hydrogen. 80% of the matter that we are familiar with in the universe is hydrogen atoms. And all hydrogen atoms act the same way. They're like twins or triplets, or I don't know. There's so trillions and billions and quadrillions of hydrogen atoms. Many more times than that in the universe. There's that many in your body, for that matter. So the hydrogen glows red. The peachy color, kind of a peach yellow that you see in a lot of the images the Hubble Space Telescope, the HST, posts online, that will be the helium, which is the second most common element in the universe. And then there's a smidge of a few other colors. There's some green, there's some blue. Blue is often produced by oxygen, forbidden lines of a doubly ionized oxygen atom. But we are attempting to focus on this fabulous collection of 4 very bright stars at the center of the Andromeda Nebula. So if we go back to Stellarium and then zoom in further.
So this is where we're going to be looking something about like this.
See, it's on the YouTube Live, it's some... Yeah, the feed is not great. Yes. So we have one of our YouTube chat participants, Martin. M42 is a nebula, the Great Orion Nebula, and I'm probably like 10 minutes behind in congratulating you on your knowledge. But yeah, and our YouTube, for whatever reason, it says that YouTube is not receiving enough video to maintain a smooth stream. We have great internet access up here on the mountain. We are in fact hardlined into the internet, so it's not a Wi-Fi issue. And it is leaving us as a healthy stream.
So this is healthy.
Yeah,
Everything seems to be all right.
yeah. Everything we can see at our end looks great. I know the last time we did this, there were a couple of issues, but they seem to resolve. This issue seems to be persistent.
All right, let's just move it back to.
So I have a log actually of when it says healthy and not healthy. It was healthy when we started. By 6:07, it said that it wasn't receiving enough video, and we thought it was because the screen looked pretty much black. 6:28, the stream was healthy. It was excellent. And 6:33, it's now not excellent again. So it may be when we're back to a dark background on our screen. So I may have to investigate with YouTube customer service, if there is such a thing, and find out if there is something we can tweak in the settings to let them know that we are looking at very cool astronomical objects, but they're dark. And there's not a lot of movement, because it may be that the live stream is looking for some motion as well. All right, so apparently the focus is coming along nicely.
I think we're just trying to center at this point.
Oh, trying to center.
Okay, and then we'll do the reveal.
And then we'll do the big reveal.
We'll start with the low gain so that we can see the trapezium, and then we'll blast it away with, so we can see the nebula. I don't understand. The refresh rate on this is really low.
So we're having a few, I won't say technical difficulties. We're waiting for things to refresh, our camera output to refresh, so that we can see if there's focus, if this focus issue has been resolved, whether we got it in focus.
Might be trying to do too much on this computer at one time.
Maybe.
All right. Okay, well, why don't we, I'm going to bring the lights up, and we're just going to look around, show people the
Okay.
parts of the telescope while Tom gets more feedback.
All right, so we're going to go back to have a look at the actual telescope dome. As Chris brings our overhead lights up, woo, and then you have to just blink a few times. And then we have this wonderful Steadicam thing that we will be able to rove around the dome and show you the dome with. So this is the roving view elsewhere in the observatory, and you can see my head, back of my head, and then go right up to the yellow ladder and the mirror itself. What's that metal stuff at the bottom? Just a counterweight?
That's counterweight.
Yeah.
And these are the other counterweights. And the bottom, are you muting?
Yeah.
Okay.
So hopefully you can hear me. We are looking at the bottom of the telescope. There's the whole view. So we're getting used to having a hand here. So that's the whole view of the telescope there.
So
We're looking at the bottom. We come into here. We have the famous green glass underneath. And so what you're seeing here is the mirror itself, but only the top side is illuminized. So it's only the top is reflecting, and the bottom, you're just looking through the glass. And the reason it's green is because it's a lot of glass. It's several inches thick. And anyone that's got an aquarium knows that if you look at a bright thing of thick thing of glass on the side, it looks kind of green. And all the stuff you're seeing through the green that looks like it's embedded in the mirror is actually just a reflection of the stuff underneath the mirror that's holding it up. Oh, I think we're going to need to turn the lights off. Okay, because we need to focus things. So we will pan back, go back.
All right, so turn the lights off.
All right.
And then we have the big reveal.
Well,
We don't have the big reveal yet. We're getting there. I'm actually going to find my hat somewhere, beginning to feel the chill. So I got my fancy hat. Let's see what the temperature has dropped to. It's 8 degrees centigrade, 47.
All right, I'm going to put the
Fahrenheit.
gain up. Oops. Let's try and turn the binning up, see if that helps speed up a bit.
All right. Seeing anything.
Change.
Nope, there's something there.
this looks familiar.
Looks familiar.
We've been here before.
We've
In fact,
looked at
actually,
this.
Because I think we're mostly focused, let's let everyone see what we're doing.
Just going to show you how we hunt for an object. Oops, and now this thing is too big. Let me make it smaller. So when the window resizes, it resizes this thing in the
Oh, does it?
OBS as well. Yeah, it's really it's somewhat annoying.
So this is our view.
Now, one thing about working on a telescope is things are often flipped. The image can be flipped north-south or east-west, and so it just seems every time we go to the controls, we try a direction and think, oops, that's not the right way, and go back the way we came.
I think a lot of that has to do with the fact that the camera, when you insert it into the where the eyepiece usually goes, it's round, so you can rotate it. And unless you mark where you put it in, you rotate it slightly, and then what had been left, right, and up and down, the last time you did it, if you've rotated it 90 degrees, well, then you're all messed up.
All right, so here we're now coming in on the nebula. And so it's not going to be the best image tonight. Again, you can see how those stars are just distorting, and they're not nearly as pinpoint-like as they should be. And to the lower right, coming in, we've got what's called the trapezium. And if it's okay with you, Tom, I'm going to bring the gain down just so that we can have a look at the stars. Okay, so I'm going to go back here, and let's bring the gain down to medium. And I have to adjust the... Oh, crap. Sometimes the controls here are ever so annoying.
Yeah,
Okay.
they don't make this particularly user-friendly. So there's, with the special camera comes special software, and the special software is not particularly user-friendly.
Yeah, so if the mirror was not warm,
Wow, that actually looks really cool,
it
though.
does look cool, but
It's just reminds me a bunch of snow angels.
yeah.
Just saying.
Anyone who knows what this is supposed to look like will just look at it and go, oh my goodness, oh my goodness. So, okay, so now we have the trapezium at, are you centering them? Okay, so Tom is now controlling the telescope to move those 4 stars into near the center. Now these 4 stars and most of the other stars that you see in this view are all kind of in the same place, astronomically speaking. And these stars are very new. They were born out of the gas that surrounds them. But up until, again, when I say recently, are we muted or are we actually on?
Here we're muted. That's coming out of the phones. No, that's
Oh, okay, that's light. Okay,
yeah.
So these stars light up the nebula, but up until recently, up until recently, they were enshrouded in this sort of gas cloud. And what happened is the radiation pressure from these stars pushes on that gas and kind of makes it get larger, and then you can get a blowing out. So what are we on? We're on the attic, right?
No, we're on Stellarium.
Oh, well,
We need to go to the attic.
Yeah.
Ah, there we are. So you can see what we're talking about.
Yeah.
We were, then somehow we did, I don't know.
Anyway, so at some point the radiation gets out and it sort of opens up, kind of like a bubble popping almost. And so we're looking down into this cavity at these stars that are very recently formed and are still lighting up the inside of this sort of cocoon that they were born inside. Okay, now what
And
we
by
can do...
recently, we're talking about how many years? Astronomically recently is as...
like about 10 million years, less than 10 million years.
Yeah, and less than 10 million years is really, really young.
Yeah. So
For
now what we're
stars.
going to do, so we're at low gain. Now we're going to bring up the high gain so that we can actually see the stuff. Oops.
Ooh,
and of
that's
course,
way too high.
I have to readjust the levels because it doesn't do that automatically. And so here now you can see the gas that's around these stars.
That wispiness.
Yeah. And are you finished focusing or are you still working on it? What's that? Never. Well, let me know when you're done because then I'll put it back to one binning so we can see. Okay. So let's turn off the binning just for a minute so that we can see the color.
Oh, happy day. It says our stream is healthy.
Oh, good.
It's, in fact, it says it's health. It's excellent. Stream itself.
Okay, so
is
now we can
excellent.
see a little bit of color.
Yes. Isn't that lovely? And that's the red, and the red is...
Lovely, and that's red. Red is.
Now you're going to wait for the
And I'm going to wait for 5 minutes until someone types it into the chat.
I'm going to rotate it down a bit. Okay.
The red is known as the alpha line, the brightest line of the most common type of atom in the universe. And for anyone who guessed hydrogen, you are correct. Ding, 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 ding. Well done. I know you guys can't see it, but I'm looking right out of the slit in the observatory dome at the constellation of Orion, or the 7 bright stars that make the constellation that most people, the pattern that most people are familiar with. It's stunning. It's just really pretty. And Betelgeuse has been a mystery the last year. It is quite bright now. It was quite dim. Stars get brighter and dimmer. I'm not sure if you knew that. And Betelgeuse last year got quite dim, and people were, well, the astronomical community was all abuzz about what was happening. But I'm looking up at it today, and it's a lovely, bright, orangey star. So there we go. That is not what we're looking at right now, though. What we're looking at is the Andromeda Nebula, which is, sorry, I've done this so many times. The Orion Nebula, M42, which is a little fuzzy light patch below the 3 stars that make the belt of Orion. So the trapezium is the very center, and that's kind of the really bright blob that you're seeing now. But surrounding that, you should see wispy, kind of pinkish red, if your monitor will allow you to see that. That's what we're seeing on our monitor here, is some reddish coloration, and that is caused by the hydrogen gas, which is the most abundant of the gases or the atoms in the universe. And the Orion Nebula is about 1,500 light years away. Yeah, something along those lines. Yeah. And this whole cloud that the trapezium is within is many, many times the size of our entire solar system. The whole cloud is huge. But it is from a cloud just like this, that our sun formed about 4.65 billion years ago.
5 billion years ago.
So it's 1,400 light years.
1,400 light years. I was pretty good. I was 1,500. Yeah, okay, so the brain still works.
And, you know, with healthy error bars, I'm sure you're actually easily within the margin of error.
One of the things, oh, we have poor streaming health again. Nuts. One of the things that is really difficult to do in astronomy is determine the distance to astronomical objects. It is pretty difficult to do here on Earth if you think about it, because if you're looking at a pine tree, for example, and it's kind of, if you're on a hike and you're looking at a pine tree and you're kind of squinting at it, and you're like, well, how big is that? Is it a baby pine tree that's close, or is it a giant pine tree that's farther away? Usually you can make a determination by looking at things that are around it. But in outer space, if there's just blackness surrounding something, it's remarkably challenging to figure out how distant an object or cluster of objects or cloud in the case of a nebula is. And there are different techniques astronomers use to do distance determinations, but they're all pretty challenging to accomplish.
So thanks to the person who pointed out we had an echo, I had the roaming camera audio on. So once again, we're not professionals.
But it does give the presentation a spacey feel.
A spacey feel?
Yes,
Okay,
smiley
great.
face. I love that. We're definitely looking into space, I can tell you that much. It's beautiful. Still chilly. I'm wondering if the temperature's dropping. No. Oh, yes, it is dropping. That's all right. We're here for only another hour. Hydrogen, yes. Martin, I finally saw the feed. It put up, you had H for hydrogen. Well done. All right. You know, it is kind of mesmerizing just looking at how the atmospheric disturbance causes what we observe to shift. So I'm looking at the trapezium now, and every second or so, things shift around a little bit. And it's not that the stars and the light output is changing. What we're seeing is the light being, or rather the atmosphere of the Earth causing the light coming from the stars to shift around.
So Tom wants to check the orientation of the camera, so
Okay.
if we can take a break on the
Oh,
view,
yes.
and you could maybe wax poetic about it.
I could wax poetic about what?
So the next thing we might look at could be the Cat's Eye Nebula.
Oh, the Cat's Eye Nebula. Ooh, which doesn't look like a cat's eye.
Yes, sir.
Oh, well, if there's light, then we can go to the inside dome view. That's much more interesting than my face.
USB?
Hey, Chris, do you want to do this? Have a view of what Tom's doing? So the telescope camera has been removed. Dun, dun, dun. Uh-oh. All right.
Okay, well, while you're doing that, I can go talk about the controls.
There you go.
Thank you. You want to mute your microphone?
I will mute.
Okay, so again, here's the main telescope looking out through the dome. And what we're going to do is go over this way to the back where we do all the controlling. Oh, and this is our filing cabinet where we keep all our eyepieces, including that monster you saw before. And this is where the magic happens. And as you can see, we've got several computers going on here. We have one computer which we use for figuring out where things are. And in this case, we're running a program called The Sky. And this is just a planetarium program that you can get. There are free ones out there like Stellarium too that you could use. And this just gives us a way to get the coordinates of each of these objects, which are in units called right ascension and declination. These are kind of like longitude and latitude, but they are attached to the sky rather than attached to the Earth. Now, once we have the coordinates, we can come over here, and these are also coordinates, also right ascension, declination, hour angle, altitude azimuth, things like that. But this is where the telescope is currently pointing. And we'll show you later how it figures this out. We have things called encoders that are on our axes of the telescope. So it knows precisely in what direction it's pointing. And then all we really have to do is use these controls here. And they have north, east, west, south. And we have buttons that control how fast. So slew makes us go really fast. Set makes us go a little fast. And then without either of those, we go very slowly. And so we can dial in where we want to go. And it's just a matter of pressing these buttons and watching the coordinates change over here and stopping when they match the coordinates of the object that we have over here. However, there's also another piece of control that we need to do, and that is the dome control. So we can move the dome left or the dome right, or if you like, counterclockwise or clockwise. Because when the telescope points in different directions, then we have to make sure that it is looking through the shutter, which is the name we give for that hole in the dome. And so as the telescope moves around, we have to move the dome around with it to make sure we can see what we want. Okay, something else, we can go around. So back up to that platform that we had before, it can ride up and down those rails, but usually we keep it down low. But you may see that as the telescope comes down, it kind of comes into the space between those railings. And that's when things get dangerous. And you have to be very careful, because if the telescope is pointing very low, maybe even lower than it's pointing now, it will be down into that, what we call the cradle. And if you all of a sudden start rotating the dome, then you could shear the telescope. You could damage it. There's also these cables that we often have to look at for. And you just have to be careful of where the dome is and be aware of where the telescope is. And of course, we're doing this at night, so things can be dark. So that's why telescope operators have to be careful. And I guess so Tom is here demonstrating the position one does when one is observing and the telescope is pointed low towards the horizon. So sometimes when we are looking at very low objects on the horizon, you have to do a bit of acrobatics to get on there. But you'll notice that he has his foot right on the back of the telescope. Now, the telescope itself weighs, how many tons? How much? 25 tons. So, 100. Extra 110 pounds. Doesn't do very much. And so you can actually almost climb right on top of the back of the telescope, which is not something you can usually do with backyard telescopes. Okay, let's come around this way. Walk around the dome. Come show you one of my favorite parts of the telescope. So if there are any amateur astronomers who are listening in, You may know what that is. That is called a telerad. And lots of astronomers, amateur astronomers, put these on their telescopes. And it gives them a kind of heads-up display with a bullseye for pointing at objects. So sometimes the telescope can get a little confused about where it is. The encoders aren't set up properly. And so what we do is we point it at a star using that telerad, and then go and dial in the proper coordinates, and then the telescope is reset and knows where it's pointing. And something else that's kind of cool. This is the declination axis. So this is the way the telescope points further north or south. And we have these things here. These are the limit switches. And you can see they've kind of got these little fingers that point down and little wheels. And as the telescope tracks, or as we move it north and south, this whole wheel starts to turn around. So you can see it's like a giant wheel. And up here, we have these blocks made of brass, I think. And so if we start to point the telescope in a direction it should not point, these blocks now start rotating down and will, one after the other, hit these limit switches. The first one will ensure that if you were going at high speed, you will not be going at high speed anymore. It slows you down. Then there's the next limit switch, which says, okay, you're really in the danger zone. We're not going to let you go any further unless you push an override switch. And then the very last one is, okay, that's it. You're not going any further. And we need these because if I zoom back here, and you see the way the telescope's pointed, if it were to come down too far, the structure of the telescope would actually hit the top of this, what is actually a tank. And we don't want that. So long before the telescope can reach that far down, those limit switches will engage and you won't be able to go any further. Now, what is this tank, you might be asking? It's pretty big. Well, it turns out that this tank is full of mercury. And the telescope, all 25 tons of it, floats on a bath of mercury. And because mercury is so heavy, so dense, that because of the amount it's displaced, it can actually take all that weight of the telescope and acts as a very low friction bearing. And we even have down here a gauge that tells us how much mercury we've got in there. And it looks like we still got plenty, which is good. All right, so how are we doing? We're back together again. Okay, so I will bring us, still the same? I don't know. Oh, we'll find out. Okay, moment of truth. Okay, we're gonna turn off the lights and go back. This time remember to mute.
Nice. All right, so we are back to going to be looking at the attic. The attic is the, ooh, that's not right.
Yeah, we need to probably adjust
Okay,
that. Let's see.
so we're gonna put you back to look at me, and I will happily talk to you while
First, we got to start it again.
Chris is playing with the software.
And we need to bring the
Oh, definitely bring the exposure up.
1 second, and then we will then get something out of here.
Woo.
Nope, no change.
About the same.
Yeah, about the same. Up, but now upside down, right? Because you clearly rotated it.
I rotated.
Okay, so we've determined that we are looking at warm mirror, not misaligned optics, I guess. Is the takeaway. Let's see, what do I want to do to make this look better?
Oh, well, let's go over to attic as well.
Oh, sorry.
Yeah.
Attic.
There we go.
Okay, so we're back. Same old.
This is where we do need multiple screens so we can see what we're doing.
It would be nice. Yeah, one thing we should mention is that one computer is doing everything. It's running our broadcast software, it's running the the Cmos camera, it's running Stellarium,
It's running Zoom.
all kinds of things. So, I'm wondering sometimes if the reason we have such a low frame rate here is because we're just asking the computer to do too many things at once. But
Maybe.
it's not like we have a whole lot of choice if we want to show everything.
Yeah.
Although the frame rate does look higher now.
Yeah,
it's
it really does.
It's definitely updating faster. So, success, I guess.
Our snow angels are dancing around. Snow angels or TIE fighters? What do you think? Kind of like TIE fighters?
Snow angels is fine.
Yeah, snow angels.
Yeah. Okay, so the next thing I think we're going to go look for
Not
is
TIE fighters.
the snowball. I think the snowball's too far west, but there's the Cleopatra's Eye.
Is that another planetary nebula? I thought we were doing the cat eye. You guys say the cat eye earlier.
Oh, did I say the cat's eye?
You did say the cat's eye
Well,
earlier.
let me look it up, and I will let you know. I think it actually is the cat's eye.
Are we going to do the inside dome view?
Sure, why not?
Why not? Let's turn the lights on. There we go. So you can see the dome again and see how the dome moves and how the telescope moves while we realign the telescope to look at a different part of the sky. And we are heading to look at the Cat Eye Nebula.
I think so. Let me just double check that. No, it's not. It's definitely not the cat's eye.
All right, it's not the cat's eye. Maybe Cleopatra's Eye, and I assure you that neither the Cat's Eye Nebula or Cleopatra's Eye Nebula look like eyes to me. They are planetary nebula, and planetary nebula form. First of all, they have nothing whatsoever to do with planets, but they form when a star, somewhat like the sun, which is a medium mass star, uses up all its nuclear fuel and kind of goes at the end of its existence. So it doesn't have enough mass to explode in a fantastic supernova like the really fancy ones do. It just kind of puffs off its outer layers in the end, and there's a white dwarf left behind.
Also
So
known
what do
as
we got?
NGC 1535.
So NGC 1535. I love the NGC as the new general catalog, new being the 1880s. We still call it the new general catalog. NGC item number 1535 is a 9th magnitude planetary nebula in the constellation of Eridanus, located east of Zaurak. It is a nice diversion from all the galaxies in Eridanus. Just, if you get tired of looking at the galaxies, you can look at a planetary nebula. It has been nicknamed Cleopatra's Eye. So this is a planetary nebula. It is the puffed off outer atmospheres of a medium mass star that puffed them off at the end of its existence, kind of end of its stellar lifetime. The white dot you see in the middle is actually a white dwarf. And a white dwarf is the collapsed core of this medium mass star. I guess you can call it this ex-medium mass star, this former medium mass star. The core collapses, there's no more nuclear reaction. This is kind of, I suppose you could say, the spent nuclear fuel. It is primarily carbon and oxygen, and it is white hot. So if you're looking at the colors of stars, red is actually quite cool, and then it goes through pretty much the colors of the rainbow. Red, and then orange, and then yellow, and then green, and then blue, and then violet. White is kind of a combination of all of these. So a white dwarf is going to be something on the order, kind of a blue-white, I don't know, I want to say about 20,000 degrees Kelvin in temperature. which is very hot. Our sun is only 5,680 degrees Kelvin? 5,860? This is what happens when I get too cold. My brain doesn't work very well. But this,
Let's go have a look and see what we got.
yep, we are having a look at the software for the camera, the Attic Horizon 2 Cmos Camera. Gotta increase the exposure time and try and find this fabulous
Object.
nebulosity.
Not seeing it.
Yeah.
Oh, yeah, there it is. There it is.
Oh, yep.
Okay, so we're gonna need more
More
exposure on this one.
longer exposure time. So we're up to an exposure time now of 3 seconds.
Yeah.
Now we have to figure out which way to slew the telescope. So what we are observing, the Cleopatra's eye, is not in the center of the field of view that we are presently seeing using the camera. So we have to reposition the telescope so that it is in the field of view, in the center of the field of view.
That's the right way.
But now that we've rotated the camera, it's like, oh, which way do we go now? So apparently it's the right way. Well done.
Now, I wonder if people are going to notice that the sky background is a little higher
It
at
is.
this point.
This is a 9th magnitude object, and in the scale of things, the bigger the number, the fainter it is. So back when Hipparchus in, I want to say 150 BCE, BC in the former vernacular, he came up with a way of measuring brightness,
Call it good. Oops. Sorry.
way of measuring apparent brightness of stars. So this isn't how much light they put out, it's how bright it appears to us. And the ones that were the brightest, he said, well, these are clearly first-class stars. And so he gave them a brightness of 1. And the ones that were not quite as bright, he said, well, these are second. They came in second place. They're second-class stars. And that's magnitude 2, and then magnitude 3, and so on. So the larger the number, the fainter they are. Our eyes, from a good dark location on the Earth, our eyes can see as faint as +6 magnitude. This object that we're looking at now is +9. So there is not a hope. There's zero possibility of you being able to see this with your own eyes. But telescopes are light collectors. They're kind of like giant light funnels. A telescope itself doesn't do anything with the light. It just collects a big column of light. The larger the diameter of the mirror, the more light can be collected. This is why astronomers like bigger mirrors, bigger telescopes, because you can collect more of the very faint light. And of course, typically the farther something is away, the more faint it is. So if you want to see really distant objects, you need a very big telescope. But this is magnitude +9, and we are having a look at it. There we go, with our camera. And you can see that the background is pretty bright, kind of the sky background. Tom, you said, what are you going to kill?
Oops. You all right?
We're going to see if turning off more of the dome lights actually helped anything. Nope, I don't think we've changed anything.
Well, one thing is we're looking much closer to Los Angeles.
The
So-
telescope is pointing toward the big city.
Yeah, so we're going to get a lot of background.
So I'm going to go out on a limb here and say I think that the upper part of the image is actually ground level.
This could be.
Yeah, so I think we're flipped upside down, or maybe even the top right corner. Whoa. Tom, what'd you just do?
Strange.
That's got rid of it. Or how long are we binning?
I didn't change anything. Let's have a look.
Because we don't seem to have background glow so much.
I think it's really lagging again. It's back again.
It may be lagging. It's a 5-second exposure.
Yeah, so let's just see. Yeah, it's changing. it's changing. For some reason, the levels just changed for some.
Yeah.
I like it.
Whatever.
I mean, I can put them down again, but
Are you getting?
I am not. I'm going to do that next. So, by the way, we said this before. Binning is you can probably maybe be able to tell if you look really closely that you can see pixels in this, and of course, the Cmos is like any other digital camera. It's got a certain number of pixels. But what you can do is you can add neighboring pixels together, which I'm going to do right now. And what that does is it actually makes the combination of the two more sensitive to the light than the individual pixel. However, we lose color. And the reason for that is because the Cmos camera uses what's called a Bayer filter. And so every pixel on the Cmos is, actually, you can think of as a 4x4 array of red, green, green, blue. So each pixel has a tiny little filter in front of it, one red filter, one blue filter, and 2 green filters. And then the software combines those together to make a real color image. But if we then start to add them up and average them, then this software doesn't take that into account, and you just get back black and white. Let's try going with a 3x3 binning. Oh, sorry, 4x4 binning. It doesn't give us 3x3. To see if that increases the... Oh yeah, I mean, you can really see that the noise in the background goes down, and the signal, which is what you're really interested in, sort of pops out a little bit more. Of course, we're still suffering from our warm mirror, so this is not as crystal clear as it could be. But I can tell you that what you're seeing is real. That is a real halo around that central star, and that's the outer layers of the star that were thrown off at the end of its life. Did you talk about the star in the center?
The white dwarf, yeah.
Yeah.
But I'm looking at an image. So if you want, obviously you guys are all online right now. If you just Google NGC 1535 and then look and click on images, you will see an image of this, and you can see what we're looking at in the feed. There's a tiny speck of light top left. That is actually a real star. Now, it's either going to be a foreground star or a background star. It's not actually part of this planetary nebula. But if you see something and you're like, is that a little smudge of something? If you look kind of around, I can see it because I know it's there. But there's the more obvious kind of inner ring. And then there is a fainter, larger bubble around the outside, in which the foreground or background star is it looks like it's kind of embedded in that. Chris is just
Playing with the levels.
futzing with the levels.
Okay, let's go to 10 seconds.
10 seconds.
I'm feeling dangerous.
10-second exposure.
10
We'll
second
see what we get.
No, this will be a good test to see how well the telescope is tracking.
Yeah. So the telescope, and you probably are not aware of this, because it certainly isn't obvious, it has to move constantly to counter the rotation of the Earth. So the Earth rotates constantly, and the most obvious effect of this rotation is the apparent motion of the sun across our sky, and all the stars and the moon as well. Everything seems to rise in the east and set in the west, but these objects are not moving that quickly. It's the Earth that is rotating underneath them. Just like, when you were a kid and you were spinning around in the school playground, it looked like the trees were flying around you, but in fact, the trees weren't going anywhere. It was you spinning on the spot. So the Earth rotates, although we see things, we don't feel that rotation, we just see things move. In order for us to track a star, the telescope has to move in the opposite direction at exactly the same rate that the Earth rotates, so that it is always looking at the same star. So the telescope, if you were to look at it over the course of time, it would actually move westward with the apparent motion of the star. to always kind of keep the star in its sight, if you would. And when Chris just said, we'll see how well the telescope is tracking, if it tracks well, then we always see a crystal clear view, and you wouldn't have any of the motion that you would get. I don't know if you've ever tried to take a photograph with your cell phone camera in low light situations when there's a lot of motion, like someone runs past, or inevitably I'm trying to either catch pictures of my kids or my cats, and all I see is kind of a blur of, with my cats, it's the tail end of the cat running away from me. That blur is because of the motion. And the long exposure time that your camera took the picture. Here, we hope the telescope is tracking perfectly, and if that's the case, then we always have a crystal clear view of the nebula. But that isn't always the case.
So now, with 10 seconds, on this screen, I can see the second shell. I don't know how well it's going to show up on YouTube, but this planetary nebula actually has, multiple shells, but the part we're seeing very clearly is sort of an internal bright shell that's easier to see, but around it, and also encompassing that other star that Jenny was pointing out, there's a fainter shell. And so this...
Wow, I'm looking at the YouTube feed. It is pretty good.
Not too bad.
Yeah.
It's a bit more pixelated because of the compression, but oh well.
Yeah.
And so this episode that the star goes through when it expels its outer shells doesn't all happen at once. You can get multiple episodes that happen over different timescales, and so you can get these different structures that come out.
Yeah, like multiple burps, if you would.
Sure. Now, left to itself, the star at the center is a white dwarf. It has ceased all nuclear fusion, and nuclear fusion is what keeps our star alive. Takes smaller, lighter elements, fuses them together into heavier elements, and that actually produces some energy. This star, when it got to the end of its life, it ran out of hydrogen in the center, and so it started fusing helium into heavier elements, including carbon. And then you get a buildup of carbon and then also oxygen in the core. And then at that point, the star just never really gets to be hot enough or dense enough to ignite the other elements that are higher up on the periodic table. And so you end up with what's called a carbon-oxygen white dwarf at the center. And it just has all this energy from the star, and over many, many billions of years will cool off like a dying ember.
Yes, but because it was under great pressure, as it cools, it actually crystallizes. So guess what a compressed, crystallized carbon ends up as?
Graphite?
No.
No, not graphite.
No.
The other crystalline
Diamond.
structure. Diamond.
And there have been examples of these cooled, crystallized white dwarfs that have been discovered. I believe the first one was in 2016, and it was found about 170 light years away from the Earth. And the astronomers, in their wisdom, called it Lucy.
All right, of course.
Lucy in the sky with diamonds. Fairly famous. So this was the star called Lucy, and it is a solidified, crystallized white dwarf that has spent approximately 3 billion years cooling down to the point that it became a diamond. Now, obviously, we can't get there, we can't mine it, but white dwarfs are about the size of the Earth. So it's a huge chunk of diamond.
And the last thing I think we can say about this white dwarf is, while cooling off as a dying ember is one of the possibilities, not every white dwarf has that final fate. It can happen that if the white dwarf is in a binary system, or if there's some other object around like another star, then what can happen is the white dwarf can attract through gravity the outer layers of that other star and kind of cannibalize its outer atmosphere. And it can build up more mass on the white dwarf. And we're not exactly sure exactly how this happens, but it turns out that if you apply quantum mechanics, so this is a completely different part of physics, right? We're talking about the physics of the infinitely small things, particles, electrons, protons, things like that. But you can apply quantum mechanics to the situation of a white dwarf. And a famous physicist by the name of Chandrasekhar found that there was a maximum mass that a white dwarf can have before strange things happen in the center with the electrons. And they just simply cannot keep the star from collapsing anymore, and it would then just collapse under its own gravity and to form what's called a neutron star. But before that happens, something else that's interesting can happen, and that is if the interior of the white dwarf gets hot enough and high enough pressure because of all this extra mass that it's accumulating from this companion star, then it can get hot enough to ignite the carbon and start fusing and making the temperature go up. But again, quantum mechanics says something interesting about these stars. If the temperature goes up, it can't expand like any normal gas would. And so it stays hot and dense, and it gets hotter and hotter and hotter. And that fusion rate just goes up and up and up, and it just can't stop. And within a few seconds, this whole one solar mass of material gets converted into heavier elements, including radioactive nickel. And that is called a type 1a supernova.
Yep. But the companion, let's backtrack here. This doesn't happen to many white dwarfs. The companion has to be very close. It has to be a very close companion, close enough that there can be mass transfer. So most planetary nebula, including this one that you're looking at, the Cleopatra's Eye, is not going to happen. This star, little to the upper left, it is either a foreground star or a background star. It is not a companion star, and this particular white dwarf will not end up as a type 1a supernova. FYI, Chris here, this is his research. This is what he does as a full-time job, studying these type 1a supernovas, so he knows what he's talking about. Well done, Chris.
I try to. Okay.
The universe is a mystery.
So I think we've probably exhausted this object.
Yeah,
And
yeah.
I guess we could move on to M31.
We could try M31.
Yeah, I'll just
All right.
double check that it's available.
M31. That's another one of these Messier objects. I would honestly say next to M42, which was the Orion Nebula, M31 is probably the most famous. So I'm going to give it a minute and see if any of you know what we're talking about when we say M31. Woo! And here come the lights again, so we might as well go back to the full dome view. All right, Chris, there's hot chocolate here. If you want,
I was just going to make my own.
not much left. Hot chocolate, it's how you get through long, cold nights.
A hint you can give is that M31 is very famous for this observatory.
Ah, yes, M31 is very famous for this observatory, but that was the 100-inch, yeah?
Yeah.
Yep, so the observations on M31, which was deduced to be beyond the confines of the Milky Way galaxy, there's a hint, that was discovered by Edwin Hubble on the 100-inch telescope. Now, this telescope here, this gigantic telescope, has a mirror that is 60 inches in diameter. There's another observatory atop Mount Wilson, and it's a couple hundred meters to the north of this dome. That houses a much bigger telescope. The mirror is 100 inches in diameter. And the Hubble Space Telescope was not built by Hubble. It is named in his honor because he was an amazing observational astronomer. He did most of his work here on Mount Wilson using the 100-inch telescope. He is most famous for two discoveries, both of which involved M31. So I happen to know that the YouTube live feed is probably about 2 minutes lagging behind what we're saying here in the dome. It's about 2 minutes for me to see it come up on the YouTube field. So I will let you guys think about what M31 is and get back to you in a few minutes. Oh, too far west. So we can't look at the Andromeda Nebula. I'm so sorry. Andromeda Galaxy. Oh my gosh. Hubble called it the Andromeda Nebula. That's why I was thinking of it as the Andromeda Nebula, the Great Andromeda Spiral Nebula. That was before it was known that Andromeda M31 was a galaxy, a spiral galaxy twice as large as our own Milky Way. Were you calling me? Possibly not. So one of the things about this telescope and this particular dome is that there are limits to where this telescope can point. It cannot point lower than 30 degrees above the horizon. So the horizon, which is basically where the sky meets the Earth, is 0 degrees. Up directly overhead is 90 degrees. And if you think about it, 90 degrees, another 90, in the back, that's 360 degrees in a circle. That makes sense. So 90 degrees at the horizon, 0 degrees at the horizon, 90 degrees at the zenith, which is the point directly over the observer's head. And this telescope cannot go beyond or below 30 degrees. So 0 through 30 degrees, this telescope cannot look at that part of the sky. It is too far over, and the way that it's built, it just can't do that. So it can go basically anywhere up here down to around 30 degrees. So we are gonna find something else to look at.
The Clown Face Nebula.
The Clown Face Nebula? That's gonna terrify people. Clowns are terrifying. Ooh, okay, Clown Face Nebula.
I'm afraid we can't leave the lights on, so yeah.
Okay. We cannot leave them on?
Not while we're observing the nebula, no.
No, not while we're observing the nebula, no. Alrighty. Oh my gosh, why am I overheating? Oh, this is my life. Temperature regulation is not my forte. Now I have to get my other mask ready. Maybe it's the hot chocolate heating me up, that's it. All right, so we're back to excellent stream health. Lovely to know. Love the slow rumble of the dome rotating.
It's quieter in one direction than the other.
It is. It's quieter in this direction. I guess if you're looking down from the top when it goes counterclockwise.
So right now the motion you see the telescope doing is from east to west, and we're moving towards the east.
From west to east.
Towards the east, yes.
Towards the east. You said from east to west.
Well, I meant that.
Never mind. Okay, we're looking eastward at the Clown Face Nebula. Is there an NGC number to go with this? So there's a comment in the chat saying that it is much better to see it in person than it is the pictures online. I mean, the pictures online are wonderful. You can't really beat a Hubble Space Telescope picture or for the planets, pictures taken by the spacecraft that have actually gone to those planets. But seeing it in real time in a telescope is pretty cool.
NGC 2392.
NGC 2392. So I'll put that in the chat. NGC 2392 equals Clown Face Nebula. Alrighty. Shall I go to the attic view? Yeah, there's nothing there. Oh. Ooh, there's a little something. Last time I forgot to change it over from the dome view, and the dome view was dark. So I'm actually going right to the attic view now.
Okay, let's see here. What do we got it on? I can't even remember. Oh, right, we're on 10-second exposure. Let's bring that down, just so we can see what we're doing. Okay, not seeing... Oh! He's still moving the telescope, that's why.
Oh. The telescope slews very quietly. So for those of you who may not be up on telescope terminology, slewing is the process of moving the telescope, either in right ascension or declination. Now, the right ascension and declination are the two components of the equatorial coordinate system, and this is how astronomers map the sky. So if you remember back to elementary school, when you did your latitude and longitude, and how you do a grid on the sphere of the Earth, where the lines kind of, what's the word I'm looking for? Coalesce, congregate, converge. There, I knew it was a C word. Converge at the North Pole and the South Pole. If you can imagine those lines, and of course the lines of latitude are all the way north and south, but if you imagine those lines kind of thrown out into space or projected into space, if you could think of the Earth as kind of a clear sphere with these lines etched on it, and then the light bulb turned on from the inside, these lines would be kind of projected onto space. And these are the lines of right ascension and declination. So right ascension lines are the ones that are like the longitudinal lines that converge at the north celestial pole and the south celestial pole. And then the lines of latitude on the Earth are kind of replicated in the lines of declination in outer space. Right. So slewing the telescope, you can slew it in right ascension, you can slew it in declination, you can slew in both at the same time. Just like patting your head and rubbing your stomach. Two different motions at the same time. So we are looking at the
Are we on the
you
attic?
just pop up there? Yep.
Yeah.
Okay, we are looking at the Clown Face Nebula, which doesn't look like a clown to me.
Well, you know, what are you going to do? Now I'm going to bump up the exposure because I'm not sure how much of that is the nebula and how much of that is our lovely mirror being.
NGC 2392.
So there's more nebulosity around it, for sure.
Oh, this is also known as the Eskimo Nebula, as well as the Lion Nebula, or Caldwell 39. A bipolar double shell planetary nebula.
Are you playing with the focus?
So often there are two,
Okay, I'll bring the
there are
exposure down
jets
for you.
coming from each pole, like a North Pole and South Pole thing. So that's bipolar flow. So this is a bipolar double shell planetary nebula. And
We're just playing with the focus a bit more.
we're trying to focus it. Clearly the effects of the hot chocolate have worn off. I'm now getting cold, so back goes the hat and the neck warmer.
Okay, let's put up the exposure. Let's go for 10. Why not? As I suspect I'm going to see much more of the see what we got. Oop, yeah, we got a. So I think there's more around it in the halo.
Yeah,
See there?
I think so.
All right, so let's see if we can find the vital discipline in this one.
Oh, I got him.
Got him? Okay.
So this particular planetary nebula is 5,000 light years away. Huh, interesting. There's two different distances that I found here. One says 5,000, one says 6,500. Well, I did tell everyone that it's difficult to determine distances. It's very far. It's thousands of light years away.
Yeah, these planetary nebulas are tricky because all the usual tricks that we do in order to figure out how far away they are to other stars really just don't work with with white dwarfs. You kind of have to know almost how old they are.
It's in my favorite constellation, Gemini.
Gemini, nice.
Yeah. Which is apparently supposed to look like twin boys, but I just see kind of a odd rectangle of stars when I look in that direction. So one of the things I will be doing in the upcoming virtual star parties that we will be having here is introducing you to different constellations or objects within different constellations. And the constellations names that are familiar, like Gemini, that's just the Greco-Roman constellation. And I don't know about you, but I'm not sure I have any Greek or Roman ancestry. There are many different sky cultures that have amazing stories about groups of stars. And of course, a group of star historically is a constellation. So there are constellation stories from the native Southern Californians. There are constellation stories from the Inuit in the Arctic, from the Inca, from the Aztec, from the Australian Aborigines. I'm having a really tough time speaking this evening. From the Chinese, the Japanese, the Korean, from African cultures. Every different culture had amazing stories about what they saw in the night sky and what they thought were explanations for what they saw. So over the coming virtual field trips to the stars, I will be introducing you to one or two constellations a night and a few of the associated sky culture stories. So I am not an expert in different sky cultures. I have European heritage myself, so I will try and explain the stories in the most respectful manner that I can. But if any of you out there are familiar with stories of the stars in your culture, please send us a message or chat it into the chat now so that I can bring those stories to light here in the virtual field trips. So how are we looking?
Well, so, I mean, I think probably you can tell that some of this that looks like a planetary nebula is just part of our dome being, a mirror being light too hot. So, be sure to come back next time
When we're
when we have a
have a better forecast. It's not a last minute thing. This particular nebula is more dim than the last one we looked at. So the last one, which was Cleopatra's Eye, had an apparent magnitude of +9.
Oh.
This
The director just went, ooh.
This has an apparent magnitude of +10.1. So this is an order of magnitude more faint than the last one that we were looking at. So let's try and figure out what that ooh was. I don't know, there's some giggling going over there on the other side of the dome.
scouring the Nicholson list.
Ah. NGC 2419.
Okay, I'm not sure what
All
that
right.
is.
I don't know what that is
So-
either.
This is a bit of a treat for us because normally we don't do our sessions this far into the winter, and so we're seeing objects that we don't get to see very often.
This is a globular cluster
Ooh, this should be interesting.
in the constellation of Lynx.
What was that? Okay, we're going to move to the object.
Yep. So we have 9 minutes left in this. Okay, yeah. It's all gone white. That's because we turned the lights on. So we have 9 minutes left in this field trip to the stars this evening. Chris is putting the ladder in its parking spot, which is a safe place for it to be while the telescope moves. I don't know if you can see it. Oh, you can. So if you follow up to the top of the yellow ladder, the far left, you will see the at the very top, the most left yellow pipe is actually bent in the middle toward the right. That's when it was in a position, Chris is pointing that out, that's when it was in a position where it got damaged. And what damaged it? Not the telescope, it would have been
I think it was the platform.
yeah, it was the platform moving. So that's why there's actually, and I'm not sure if you can see them, yeah, possibly, some yellow squares on the floor. Chris is tipping it down. Yeah, so the wheels are supposed to be in those yellow squares, and that's when you know that the telescope, or the ladder rather, is in a position where it is safe and it will not be hit by anything.
Just going to turn down the exposure and stuff. So.
Keep talking.
Well, we are heading to a globular cluster. Hopefully we'll be able to see this. This is a globular cluster that is very, very far away. So if you guys know how big the galaxy is, the Milky Way galaxy, the disk of the Milky Way, the visible component, is about 100,000 light years side to side, which means it takes 100,000 years for light to get from one side to the other. And he's turned off the lights on me. Oh, but you can still see my hands from one side to the other, the other. One side to the other. So now we've got a little tiny Milky Way. Anyway, this globular cluster is 300,000 light years away. So it is extraordinarily distant, but it's not along the plane of the Milky Way. Globular clusters are either above or below the plane of the Milky Way galaxy. They are in the halo of the Milky Way galaxy. And let me have a look here and see how many approximate stars are in this. So globular clusters are very old groupings of stars. And we know they're old because they don't have any of the brighter, bluer stars that are newly formed stars. So typically globular clusters are predominantly yellow and orange and red stars, and these are the stars that last the longest. But in a cluster of stars, and they all formed at the same time from the same giant nebula, giant molecular cloud. The largest stars burn through their nuclear fuel fastest. They're hottest, they burn through their fuel, they go supernova, they go out. And over the course of time, you end up with only these dimmer, more orangey red stars. And all of these globular clusters that are above and below the plane of the Milky Way galaxies, these are the ones that are the very old stars or old collections of stars. And I'm having a look on some websites that I go to see if I have any indication of how many stars are in this cluster. So this cluster is an estimated 12.3 billion years old. That's when the stars first formed. Just about 1.5 billion yeah, 1,500,000,000 years after the formation of the universe itself in the Big Bang event. 12.3 billion years old, and we have approximately 900,000 times the mass of the sun. Now, because the stars are the stars of the globular cluster are less massive than the sun, for something to be about the comparable mass, 900,000 times the mass of the sun, but the stars themselves are less massive than the sun individually, then we're looking at certainly over 900,000 stars, over 1 million stars, possibly millions of stars, most probably millions of stars. So this cluster is going to have millions of stars. It's incredibly old. The apparent magnitude of all of the light coming from all of the stars and the cluster itself, the apparent magnitude of the whole cluster is +9, which is about the same as the Cleopatra's Eye, which is what we saw as the first globular cluster, or the first planetary nebula. What else? Okay. Using the wrong mouse on the wrong computer. 300,000 light years away from us. The right ascension, 7 hours, 38 minutes. Declination is +38 degrees, 52 arc minutes. For those of you who like coordinates and mapping, I love maps.
Let's see if we can.
It's like a treasure hunt every time I look at a map.
We're in the right place, but we're not seeing a whole lot.
We are not seeing a whole lot. Do you want to put it on the attic view so
Yeah, sure.
people can see what we're now seeing?
So they can see what we're not seeing?
Kinda, yeah.
Maybe east and west a bit? Go west.
It's also known as Caldwell 25.
Let me bring the exposure down for you again, since it's at 5 at the moment. Oops. Gotta be careful with that mouse. Meow. Yeah, I was just about to do that. Well, it certainly helps with the noise. All right, I'll check one more time with coordinates.
In fact, if you're okay, I'll just, yeah, I'm good. Zero in.
Yeah, we have nothing. And we have 1 minute left, gentlemen.
Okay, pressure's on.
Pressure's on. Maybe we'll go 1 minute past our 8 p.m. cutoff time for the 3 viewers we have with us this evening, of which I think I am one. Those are the coordinates. Okay, so this is a dud.
Okay, let's. All right, let's bring up the exposure time. Let's go
Can we
for
zoom
broke.
out?
I think we are zoomed out entirely. Okay. We're at 4 binning. We're at exposure time of 10 seconds. High gain. This should.
I'm not seeing a globular cluster.
Yeah, I think it's there. It's just very faint.
Yeah. Wow, right in the middle.
It's extremely faint.
Wow. Okay, so it's taking up pretty much the entire middle.
Yes, it's big.
Yep.
I mean, it's big in this field.
Because it's 9th magnitude, but that light is spread out over a much bigger
Yeah.
area. So, yes, it's coming in.
All right, let's go to 15 seconds. I guess, you know, we're again, because our mirror is not cool,
Yeah.
It's cool, it's just warm.
it's just warm.
It's
yeah.
just warm. It's totally cool. It's awesome.
But it's just, because we're not getting very nice point-like stars, the light gets spread out, and so, you know,
Yeah.
all right.
So you can see something that looks like spray paint.
Wow. That is a faint globular cluster.
That is. Well, it's 300 light years away. 300,000 light years away. It's
Okay.
incredibly distant.
Can we bin it more? Oh, okay, binning by 8. Binning by 8. This ought to be interesting. Let's see
Yeah,
how
we'll
this
certainly
goes.
get no color, but we're not going to get color to begin with.
Okay, we're
Well, we
on-
see something.
Yep.
Our audience will not leave disappointed.
And that brings us to another point, and that is that this is not globular cluster season. And the big discovery that, binning by 8 really increases the. I can't tell if that helps or not.
Yeah, a little bit, I think.
Yeah, you can sort of see this. Anyway, so the big discovery that this telescope made by Harlow Shapley was that when you look at stars in the night sky, they're all sort of gathered together in the Milky Way. And so you get this idea that we're living in a sort of a pancake-like structure of stars, and that's the Milky Way galaxy. But when you look at globular clusters, they're all kind of in one direction on the sky. So right now, the position that the Earth is around the sun, most of the globular clusters that we like to look at are in the direction of the sun. And so we can't look at them now, they're below the horizon. We've only got this one stray globular cluster that I understand why we don't go to it very often. And so this told Shapley that we're probably not at the center of our Milky Way galaxy, with the assumption that you see globular clusters randomly in all directions in the Milky Way. Then the fact that you see them all in one direction means that the center of the Milky Way is off in that same direction. We actually have a prop that we can show when we bring the lights up.
Well, we could, but it's also 8:03.
It's 8:03,
So I
oh
think our
goodness.
audience may have other things to do at 8 o'clock. So I think this brings an end to our observations this evening.
All right, so I'll bring it back to the inside dome view. Go turn the lights on.
So there we go. I guess we can say thank you very much for joining us this evening. We will be back, weather permitting, in 2 weeks on February 16th of 2021 for another evening of looking at fabulous astronomical objects. I hope to see you then.
Bye. All right. Ha. Well, at least we only embarrassed ourselves.